Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. Couple notes here. First of all, the camera glitch. If you are having a camera glitch, from what I understand, sometimes a few of you have said that you do at the beginning. Bear with it for a few seconds, and apparently it clears up. So the question that we're handling today is what type of loads do the different connectors transfer in the connection shown? So this is kind of a question that came in from one of our young engineers that was more conceptual in nature. All right, so let's see. So the title here, you can see that part of the title is WR1. So there are other Bridging the Gap tutorials that we have related to WR1. So you can search for that on our channel. You can search for WR1 in our channel, and you'll see kind of other tutorials that are related to this. So this doesn't cover everything regarding this detail, but it covers the conceptual part of it. All right. Get all you can from the tutorial. Don't jump around. Kind of a bit of advice for younger engineers. You know how sometimes you just want to pick off a value, kind of go into a book and pick off a value and not be bothered with how that value was obtained or whatever. You're just shortchanging your education, right? The more you can understand the theory behind it, the more you can understand how a structural engineer thinks, the sooner you'll get to be thinking like a structural engineer. So don't shortchange yourself. Listen listen and absorb the whole tutorial. Take notes if you need to. Thumbnail parts of the tutorial so that you can kind of keep track of at what point in the tutorial different things were said. But don't shortchange your education. Okay, let's look at the detail, and I think you should be able to see this pretty clearly. So here's the detail. Let's cover the assemblies that we have here. So we've got a stud wall assembly, all right? So that in essence, scroll up a little bit, is this part of it. Okay, so that's our stud. We have a lumber stud assembly here. You can actually see that there are, clear that, zoom in a little bit. Because if we zoom in, one of the things that you should be able to see is that we have a double top plate there. Okay, so that's how we represent a double top plate. Double top plates serve multiple functions for us as structural engineers. So that's covered in other tutorials in Bridging the Gap. If you have questions on that, leave me a note at the end of this tutorial, and by all means, I'll try to point you to the right direction on what tutorials to look for to cover that material. So there's a double top plate, but the importance of that then is that, let me see if I can clear and zoom back out. Is that then we have literally in this wall assembly, we have two studs. So there is one stud that goes above the double top plate, and then there's the stud that's coming in from the level below up to the double top plate. Okay, so we have kind of two separate elements that make up the overall stud wall assembly that we see here. All right, now, and then we've got a wood structural panel shear wall. So well, it's harder to see, but basically, right here, well, right there is where the wood structural panel is, what we used to call plywood. There's the wood structural panel. So you can see it there. All right, so we've got a wood structural panel on this wall assembly. What else do we have here? We have roof framing, yes. So the roof framing is this assembly right here. Okay, so we've got roof framing. Again, we've got a wood structural panel diaphragm. So here's the wood structural panel right here. And all together, the wood structural panel, these blocks right here, those blocks, which are explained in other sessions in Bridging the Gap. So again, just search for those, or just drop me a note and I'll see if I can point you in the right direction. But all of that is the diaphragm assembly. All right. Then here is a diagonal brace. All right, so we have a diagonal brace there. Let me see if I can now. All right, the brace, brace load, the purpose. What's the purpose of the brace? All right, well, that might not be as obvious if you are a younger engineer. But be aware that one of the forces that we have to resist when it comes to walls is wind out of plane, what we call wind out of plane forces. It's what the building code will refer to as a component and cladding force. That's covered in other tutorials in Bridging the Gap. So again, let me know if you have questions on that at the end of this tutorial, and I'll see if I can point you in the right direction on the Bridging the Gap tutorials that cover some of those aspects. Okay, so here I'm illustrating for you the wind forces acting on this wall in the direction that is out of plane to the wall. So we've labeled that here as W. We've labeled it as W. And keep in mind that these forces are reversible, right? The wind pressure can be a positive pressure, it can be a negative pressure. To get more into that, there's other sessions in Bridging the Gap that cover that. So by all means, again, if there's a specific question in one of those areas, let me know and I'll try to point you in the right direction. So here is the force acting out of plane to the wall. All right, now let's get back to our friend here, the double top plate. Again, the double top plate is covered in other sessions, but basically what that does for us in some respects is, let's look at that wall assembly. So here's our stud assembly. I've drawn this now as a straight line, but the reality is, or I'm sorry, yeah, I've drawn it as a continuous line, but the reality is that this double top plate introduces a hinge here. So literally, okay, so we have a simply supported beam represented by the red line segment, right? We've got wind pressure pushing against our beam. And again, that can go from left to right or right to left. It can be positive wind pressure, negative wind pressure. We've got our simple support, which, let me see. So here we've got a simple support. Here we have a simple support, but then here's the problem, right? We've got a hinge in the middle of our beam. Our beam is unstable. So the double top plate, in a way, here introduces a problem. It introduces an instability for this beam. So what we need to do is add this brace in order to take the horizontal thrust. You know what, let me do that the other way around. Let's see if it's more intuitive. Right, we introduce our brace to take the horizontal component at the hinge to eliminate that instability. Okay, so that's what the brace is doing. Now the question is, does that brace take does it resist does it resist a moment, or is the load in the brace an axial load, right? All right, and there I've drawn it in for you. So in blue, right here, in blue, there's our moment representation, right? What did I draw? Clockwise moment there. And in yellow, I'm showing you an axial force. And again, it could be, it is reversible. So depending on the direction of the load, that axial load will act in compression or in tension. So that's the question. Does the brace carry flexure, or does the brace only carry axial load? So I'll let you think about that one for a second, and then let you know that the brace only carries axial load. Now, the next thing that we need to do here is resolve the forces in the brace. So we've got a diagonal force, and this goes back to, gosh, what, third year, junior year statics, right? Remember good old statics, your structural analysis class? So we've got a horizontal component as our reaction at the reaction at the end of the brace, and we've got a vertical component, right? And again, those loads are reversible, so depending on the direction of the load, that'll dictate what direction your two components are. But we do need to resolve the forces in the brace. Okay, so now let's go ahead and focus on the top part of the connection of the brace right here. Let's clear this all up, and let's scroll down. Okay, so here's the top part of the brace. All right, so again, we've got, change here. So again, here's our sheathing. Here's our wood structural panel. Here are roof rafters. And if that terminology, roof rafters, joists, all of that is unclear, I think that's covered in other tutorials in Bridging the Gap. So you can find those there. What else do we have here? We have some blocks, right? And I believe I already said this is covered in other sessions in Bridging the Gap. And here is our diagonal brace, right? Now, what might be harder to see is we have nails here that are connecting the brace to the block, right? Might be harder to see, but that's the idea. So we want to connect the brace to the block with nails. All right, let's see if we can pull back a little bit. All right, nail capacity. Okay, so for this connection that I just described, the nails connecting the brace to the block, as far as that calculation, that capacity, that load transfer, the actual numerical load transfer is covered in another tutorial in Bridging the Gap. Look for that WR1 in the titles of our tutorials. That will be other tutorials associated with this detail. All right, load paths. Because again, we're trying to focus on the concept of how the detail works, how the connection works. The block to the roof joist, okay, I get it. So let's scroll back down. All right, so we know that the brace, let's just focus on one direction for now. The brace is, hold on, let me think about that one for a second. Yes, I'm showing this correctly. Between the out-of-plane force of the wind acting from left to right or right to left, the one that we're more concerned about probably is going to be when it's acting from right to left, what we would call negative pressure. And in that direction, that's going to cause the brace to pull down on the blocking. It's going to create a tensile force in the brace. And by the way, the design of the brace due to an axial load, again, is covered in another session. So I'm not going to get into that here, but we do have a downward component, excuse me, acting or a downward component transferring from the brace into the block. Okay, so we have this downward acting force on the block, right? So here's where our value as structural engineers really comes in, right? Our ability to visualize loads, to not lose track of them, if you will, to resolve them, to know where they go. At the end of the day, we need to provide support for all loads, right? We need to be able to transfer loads from one place to another until finally, in whatever way, we are able to dissipate them. And by dissipating, typically that means getting them into the foundation. But we can't lose track of our load. So here we have a downward acting load from the brace into the block. Where does that load go, right? So we do get it from the brace to the block through the nails, but now it's in the block. Now where does it go? Well, where it goes is we need to then get this load to migrate over from the brace, from the nails, into this rafter and into this rafter. All right, we need to get the load into the rafter. Now, that doesn't happen by magic, right? Doesn't happen by magic. So what we're not showing here is there does need to be some connection. There does need to be some connection between the rafter and the block to transfer that load. Sometimes it helps me to kind of exaggerate things, and that helps me visualize. So let's just say hypothetically, there is no connector between the block and the rafter. In fact, let's assume, I don't know, let's assume that block, what if we made that block out of ice, right? Very slippery piece of ice there. Then would it just slip down? Sure, right? We need to provide a connection. Otherwise, that block is just going to slip down. And certainly when we pull on it, it'll just slip down. So we need to provide some kind of connector there. That's not the purpose of this tutorial. I'm sure that's covered in another session in Bridging the Gap. But we do need to provide a load transfer there. But the idea is that then the load does migrate from the block into the rafters. And the rafters do resist vertical load. So we would cover that vertical component by transferring the load into the rafters. Now let's take a look at another part of the detail here, which we really haven't talked about. You might see that there's a nail there, and there is a nail here. Not shown, but there's a nail over here too. So what are these nails doing? Well, those nails, even though we're only showing one, the reality is these nails are repetitive. So there's going to be another one here, maybe another one here. Every so often, we're going to have nails that connect the wood structural panel component of the diaphragm to the blocks. And typically, the way we specify those nails is by calling, those are what we typically refer to as diaphragm boundary nailing. And typically what you might see is maybe 10 Ds at, let's say, 6 on center, all right? So every 6 inches, we're gonna have a 10D nail connecting the block to the wood structural panel. And this is part of diaphragms. We're not getting into that in this tutorial. That's covered in other tutorials. Again, drop me a note if you have a question on anything specifically here, and I'll try to point you in the right direction. But but we have nails, repetitive nails, that connect the blocks to these blocks to the wood structural panel. Now, the next thing that we need to think of is that these nails have a finite capacity, right? This load transfer between the wood structural panel and the blocks through the diaphragm boundary nailing has a finite capacity. Again, capacities of diaphragms is covered in another tutorial or other tutorials, but there is a finite capacity. So let's just say that hypothetically, our brace imposes an 850 pound, let's just say 850 pound force. Okay, so our brace is transferring, is putting into the block 850 pounds. Now, I didn't want to do that. So we have a resistance that we can resist in the nails that connect the sheathing with the block. We are able to resist, let's say 300 pounds. I'm sorry, 300 pounds per foot. 300 pounds per lineal foot is what we're able to resist through this sequence of nails that we have here. Remember the 10Ds at 6? Well, gosh, I don't have to be too bright to see that I've got a problem here, right? I'm putting in 850 pounds into this block. I'm resisting 300 pounds per lineal foot. And if we assume that we have a typical spacing of rafters, which is typically 16 inches on center, little over a foot, gosh, I'm not going to make it, right? I don't have enough resistance in my load transfer from the block to the wood structural panel to the sheathing to resist the 850 pounds. Got a little bit of a problem here. Well, gee whiz, now what can we do, right? Well, here's the thing. Here's another part of this assembly that we haven't discussed. Take a look at these gray lines down here. Those gray lines are steel straps. So we've got a steel strap that connects. If we could pretend the brace isn't there for now, we've got a steel strap. We would be able to see this. We would be able to see a steel strap that bridges over that rafter and connects one block to the block that the brace is connected to the adjacent block. And the same thing over here. And yes, what we're not showing is that the strap gets nailed in. So this strap has nails, multiple nails that go into this block, and this strap has multiple nails that goes into this block, and the same thing over here. These are steel straps, and I believe steel straps, and there's some design examples in other Bridging the Gap sessions, so I'm not going to get into the numerical part of this, but basically we've got steel straps. Steel straps are good intention, all right? So, so what this does is it allows for load sharing. Whether we want to use the term load share, or you're more comfortable with dragging, however you want to visualize it. But what it allows us to do is to pull some of the load that's in this block that we are not able to resist through the nailing here. It allows us to pull it out of this block into this strap and into the adjacent block. And the same thing over here. It allows us to transfer some of the force from one block to the adjacent block. And now with that, then we can activate the nails that connect the next blocks over. And we can activate these nails. And you can do that over multiple to bridge multiple blocks across multiple rafters. It just depends on your load, right? How much load you have to dissipate will dictate how much load you need. Yeah, will dictate how many blocks you have to put in and how many blocks you have to strap together to ultimately get enough nails up here at, what did we say? Here it is, at 300 pounds per foot to resist the 850 pound load that we have, right? So in this case, what, if I do some rough math there, what are we talking about? Maybe 3 feet, right? 850 pounds, 300 pounds per foot. I need roughly about 3 feet of blocks strapped together to resist this. So again, doing some quick math, 3 feet would be what, two blocks at 16 on center would give me 32 inches, and probably not quite enough, but 3 blocks would give me 48 inches. And so that's, in fact, so the way we're showing it here is probably the way we would actually need to detail this. It would be 3 blocks, 2 straps to be able to resist 850 pounds of horizontal force being transferred from the brace into the block. Any questions on that, by all means, let me know at the end of this tutorial, and we'll see what we can do to cover it for you. Okay, now let's move on to another aspect of the load transfer that we need to do here. So let me clear the screen, scroll down here. Okay, all right, so now we need to focus on this guy here. That is a hurricane tie. The hurricane tie is good to resist tension. So let's see if I can do this. So right across, I didn't want to do that. So right across the middle of that hurricane tie, again, the hurricane tie is this light gray line that you see here. And let me see if I can kind of freehand draw it for you. So basically what you're looking at is what's shown down here. What's shown here is this. What this has, and it's not drawn in, is nails that go from this flat plate of this tie into the stud right here. And then the strap, the hurricane tie, twists and turns, and then it becomes flat in the other direction. So then what you have here is nails going down. So the hurricane tie allows for nails on each side of it to go in a perpendicular direction. You see that? Here the nails are out of our plane, and here the nails are in our plane. And it allows for a tensile load transfer there. All right. I don't know, that might be covered in another, probably is. It's covered in another tutorial in the WR1 sequence. If you don't see that, let me know if you need to take a look at that. All right, so the hurricane tie provides tensile resistance. Again, what we're focusing on is wind pressure perpendicular to the plane of the wall. And the hurricane tie resists the negative wind pressure. So remember, we've got this, I don't want to do that. Let me see if I can get an arrow here. Here we go. We've got wind pressure that's pulling out on the wall, right? So we want to keep that wall assembly tied into the roof diaphragm. We don't want them to separate, right? So we need to transfer this force, pull this wind force back we need to pull it back into our diaphragm. And that's what the hurricane tide does. All right, so it keeps the wall from pulling away from the roof diaphragm. Okay, so that's the hurricane tide. Again, any questions on that, let me know at the end of this tutorial. But let's move on to the next aspect, the next part of the load transfer here, which we haven't covered. Right in here, there is a nail there. There is a nail here, and there is a nail here. So hopefully you see that we have 3 nails there. 3 nails, and if I overlap them, there's a nail here, a nail here, and a nail here. All right, let me clear the screen for you. So we've got 3 nails there. So now let's discuss their purpose. There we go. Are they resisting vertical load? Okay, well, vertical load, how? Let's see. Got to figure not into the stud, although we can't see what's supporting the stud below. But let's assume that there is some sort of support, whether that means that the stud is landing on the floor below or the foundation below. Let's assume the stud is supported. And then here we certainly have a rafter. So the rafters are supported at each end. So really there's no vertical load that we're trying to transfer here. That would not be what your intuition should tell you, that these nails are here for. So are the nails there for some kind of lateral resistance? And the answer to that is yes, they're there for lateral resistance. Now let's just assume hypothetically that, that the hurricane tie was not here. All right. So we have no hurricane tie. Now what? Well, now without the hurricane tie, we probably would be depending on these nails here and here to resist that out of plane force on the wall that wants to pull the wall away, right? But there's a problem with this connection. Think about it. See if you can come up with it. The problem with this connection is that we would be using what we would call nails in withdrawal. And I'll even write that out for you. So we have nail, well, I'm going to draw it out in yellow just to not switch, but all right, we would have nails in withdrawal. And let me right away cross that out. We do not, as structural engineers, we do not like nails in withdrawal. The capacity that a building code gives us for a nail in withdrawal is very low. More times than not, what we're going to find is that nails in withdrawal is not adequate. Plus, there's a certain, I guess, bias towards a nail in withdrawal, and that is that ultimately, as you activate the nail in withdrawal and go through cycles of it being loaded, unloaded, loaded, unloaded, eventually it starts to wedge out, which causes tearing in the roofing, depending on what other assemblies are going on around it. So just in general, we try to avoid using nails in withdrawal. So if we didn't have the hurricane tie, then yes, we would clearly have to depend on the nails in withdrawal to be able to transfer the load tension, the load that pulls away the wall assembly from the roof assembly. But we do have the hurricane tie, so that's a moot point. So what we are transferring with these nails is the diaphragm force. in and out of our plane here. So let me see. I'm going to represent that with a circle and an X through it. What that means for us in structural engineering is that's how we represent a force going into the page. Think of it as an arrow. We're seeing the butt end of an arrow. So it represents a force going into the page. So that's the diaphragm force that we have here that we need to resist with this nailing assembly that we have here. So what we've got is the force in the diaphragm, right? So here it is running towards the end of the diaphragm, and it gets to the end here, and it'll go through this nail into that rafter. So we've got a nail right here, right? And again, that is a so that's diaphragm boundary nailing. That's nailing that occurs every 6 inches. Depends on the design of the diaphragm. It depends on what you dictate to be the capacity or what capacity you need. That'll dictate the spacing of the diaphragm boundary nailing. But that's your diaphragm boundary nailing. So with that, then we've been able to transfer the load from the diaphragm through the diaphragm boundary nailing, and now it's in the rim joist. I'm sorry, this isn't really a rim joist. Now it's in this rafter. All right. So now what? Now where do we send the load? Well, that's where we add then this nail here, right? So we'll add that nail. I'll draw over it. So that's a nail right here. And what that does then is transfer the load from this rafter into this element. All right, so keep that in mind because I'm going to clear the screen. So now the load, that shear load that started in the diaphragm is in this element here. That's a block. That's a block between the studs in the wall assembly. Now we've gotten the load into the block. Okay, now what? Well, now from the block, we use this nail that I'm going to draw over. So there's a nail right there. Let me see if I can erase that. So that nail, we're going to transfer the load from the block through this nail into this element. And that's the wood structural panel of the shear wall. That in essence completes the load transfer from the diaphragm here to the shear wall here. Okay, so your load transfer was from the diaphragm, it goes into the diaphragm boundary nail, into the rafter, through this nail into the block, and then through this nail into the shear wall. And then it goes down its merry way, and you know, how then we resist the load as it gets below is another detail. It's another session, but that's the purpose of the connectors that are in this detail. Okay, so let me clear this and let me move on here. And yeah, that basically clarifies in everything. That's the load path that's present in the detail that we were just looking at. That explains all of the assemblies that we had there. Again, if there's any questions, leave me a note at the end of this session, at the end of this tutorial, and we'll try to point you in the right direction or answer that for you. If this was helpful to you, sure appreciate you leaving us a thumbs up. If you have any comments or suggestions that would make this more transparent, more clear for you, by all means, let us know. Leave a note in the comment section at the end. And if this was helpful for you, certainly feel free to subscribe to our channel. That way you will be notified as new tutorials are added to our channel. Okay, real good, guys.